Hello and a really big warm welcome to this presentation from the Urban Penguin. My name is Andrew Mallett, and in today's presentation we're going to be taking a look at the wonderful world of binary and bitwise operations. Now, a lot depends on what you do with your programming career, whether or not you're going to need this, but certainly getting ready for the PCEP, the Python Certified Entry-Level Programmer, this is one of the topics for 1.4. So come on, let's get our feet dirty and dive straight away into learning about our bitwise operations. Our first calling point on today's journey is going to be the Bitwise Not Operator, represented by the tilde symbol. Now, when we're working with bitwise operations, pretty much everything is going to be converted across to binary, but we can still work with decimal numbers. So here I can set x to have a value of 5 in decimal. And then if I use tilde x, we're using the Bitwise Not Operator. This flips all of the bits, making the number a negative number and adds 1 to it. So the process itself is relatively complex and is known as our 2's complement. But if we go through and look at what's happening in simple terms, if I put some raw code in here, just so I can type in here, x equals its negative value, and then x plus 1. So if x starts off as a positive number, it's going to become a negative number. If it starts off as a negative number, it's going to become a positive number. Here I can go through and have x equals 0, tilde x then becomes negative 1. And our second calling point is going to be the Bitwise And Operator, which we can use with the ampersand symbol. When we go through and take a look at this, there might be more practical examples. From a networking point of view, this is the process of how an IP address is resolved to be on a subnet. But let's take a look at the very basics. We can have x equaling a value of 6. Y we can have maybe equaling a value of 5. If we try and AND these two numbers together, we will go through and take a look at them in binary, and where we have a 1 compared with a 1, then that is going to produce a 1. Everything else will produce a 0. So if I look at x and y, our bitwise AND operation, we get 4. Now you can say, well, how do we get 4 by ANDing those together? Remember, we're looking for corresponding 1s in binary. So when we look at the values in raw binary, having x as 6, we would have x equals 1, 1, 0, a 4, a 2, and no units. When we look at 5, this is going to be a 4, no 2's, and a 1. The ANDing operation then is going to look at the two values and compare where we have 1s. Where we have 1 in both x and y, we get a 1. So the first compares to 1, the second compares to 0, as does the third. So we end up with 1, 0, 0, which is 4 in binary. Have a practice with this, and it's really not that difficult, but we'll run through another example so we can get a better idea of this. We don't need to use variables, and if I just use, say, the integer 8, so the value of 8 in decimal, and then I can go through and use the AND or the ampersand symbol and have this ampersanded with 4. Now, we might think they will have bits in common, but when we look at it, we get 0 coming back. But when we enter a little bit further, we're going to realize that there are no elements that they have in common where there is a 1 on both sides. When we look at 8 in our raw text, that's going to be 1, 0, 0. So that's our decimal 8. When we compare that through the ANDing operation with our decimal 4, we've already seen that our binary version of 4 is 0100, so that's our decimal 4. When we try and compare then to see which bits are equal to 1, we don't have any where we have the commonality of 1 on the top and bottom. Our next calling point at this station is going to be the bitwise OR operator, denoted by the vertical bar. Now, where we were looking at ANDing, they both had to be 1. When we're looking at OR, one or other, or even both of them, could be set to 1. So if we go back to having our X being 6 and our Y being 5, and then when we look at ORing these together, so X ORed with Y, and look at the corresponding result that we're going to get, we're going to see that this is going to come back as 7. And again, you're going to look at it, why did we get this bizarre number 7? Well, it all becomes quite clear when we look at the binary values. So when we look in our raw text here, we can go through and put 110. This would be our value of 6. 101 is our value of 5. But we're looking with 3 bits for both of these numbers, and we can see that there is a 1 for each space, either top or bottom, or even both. So the result is going to be 1, 1, 1. I do hope you're enjoying your journey with us. Our next stop is going to be the Bitwise Exclusive OR operator with the caret symbol. So let's stick with the same numbers that we were working with before, our variable X and Y. So X caret Y, X exclusively ORed with Y, gives us a decimal value of 3. 3, I hear you say. Well, let's go back and just take a look at what this means. Where we compare our 6 with 5, 1 and 1 is not exclusive. So they are both set to 1, so that's a 0. Then we have 1 and 0, well, that is exclusive. And then we have 0 and 1, exclusive again. And our final calling point today is the Bitwise Shift operator. This could be the left or right shift operator. So let's take a look. This is where we can adjust the size of a number by adding or removing trailing zeros. So if we have X assigned the value of 5. With this set, we can then go through and have X left shift by 2. So we're going to move all of the numbers across 2 places to the left, adding in the trailing zeros. When I look at the result of this, it's going to be 20. We get a larger number. Hopefully we could do with this on our salary and our paychecks and get ourselves a quite larger number. But let's see what's actually happening when we do this. We know that X is 5, which is going to be 101. So that's our decimal 5. When we go through and left shift by 2, we're moving everything across to the left by 2 places and then filling out with zeros. So it becomes 10100, which is then our left shift by 2, or our decimal 20. Our leftmost bit is a value of 16. Then we don't have any 8s, we have a 4. 16 and 4 gives us 20. Let's take a look at another example. If we set X to a decimal value of 10, but this time let's work out what the value is going to be rather than have Python calculate it for us. So we can go through and set up another cell that we can work with and put in some of our raw text data. So let's go through and make sure that we set this up to be raw. When we look at our decimal 10, that is going to be a value of 8, followed by no 4s, a value of 2, and then no unit. So 1010 in binary. So that's our value of 10. Well, if we left shift this by 2 places, it's going to be 101000. Looking at this number, the very left number is a value of 32. Then we have 016s, but we have 18 and then no other values. So we're going to get a value of 40. So at least that is the theory in any case. Let's go through now and see if Python comes up with the same answer as us. So we can go through and specify x left shift by 2. Take a look at that, and we did get the sums right. It is 40. But just in the same way we can move to the left 2 places, we can also correspondingly move to the right 2 or more places, especially if we have to put numbers back to the way that they were. So if I go through then and have my x being assigned the value of 40 now, we know what it's going to be if we right shift it by 2 places. It should then return to our original value that we had of 10. So let's have then x and right shift by 2 places, and then we get 10 coming back.
All that is left to say is thank you for watching. If you've enjoyed this, then you are probably sadder than I first thought. For more of this drivel, please subscribe, like and comment to @the Urban Penguin.